Okay, guys, a little introduction to energy, work and energy. When we did the lab where we ran up and down the stairs and measured our energy and power, we already calculated our work. It was our weight times the height of the stairs we ascended. And of course, power is that amount of energy converted per unit time in seconds measured in watts. Okay, so I won't review power in watts, but just to review a little bit, work is force times distance. Okay, and of course this is measured in joules, abbreviated capital J, because Joule was somebody's name. And it's actually, if you recall, force is measured in newtons, which is a kilogram meter per second squared. And if we multiply that by distance measured in meters, a joule is equivalent to a kilogram meter squared per second squared. Okay, so for those of you keeping track of the units at home, and I hope you all are, that's what's going on. So what we'll do first is we'll take the force, and the force we're concerned about, since this is mechanical energy, we're going to get to gravitational potential energy first. And since gravity works up and down, of course the force we're interested in is the weight. And keep in mind that's a lowercase w for weight. And the distance we're concerned with is the height, because that's the direction in which gravity works. And if we refine this a little more, the weight is actually mass times gravity. And of course we just bring the h down, and we have a formula for gravitational potential energy. Okay, so there's our first formula. Okay, so what to do next? Well, if we take into account that h is like the y in the shoot the monkey problem, or the shoot the monkey gizmo, where it's 1/2 gt squared, where g is an acceleration, the acceleration due to gravity in this case, t is time, and I think in the shoot the monkey gizmo, h was y. So what we're going to do is we're going to plug this into here, and we're going to get mg times 1/2 gt squared. So that's a little bit inconvenient. So what I'm going to do is I'm going to rearrange some stuff. I'm going to pull out the 1/2 from the parentheses and put it in front of the m. I'm going to bring the g into the parentheses, and g times g is g squared, and I'm going to leave the t exactly how it is. And one more step, 1/2 m times gt squared. Okay, now I'm going to resort to the first kinematic equation, which says that the final velocity is equal to the initial velocity plus acceleration times time. Here the acceleration is again the acceleration due to gravity. So instead of using a, I'm going to use g and multiply by time. I'm going to assume that, not making this any more complicated than it needs to be, that this started from 0. Okay, so where I have the GT, I'm going to plug in velocity. So this is 1/2 mv squared. And this is the formula for the energy of motion or kinetic energy. Okay, so we've got gravitational potential energy, we've got kinetic energy now, and of course up above we derive this all from work, which is also energy. We generally call it work when energy is put into something or taken out of something. Okay, so work is kind of energy in transition. So that brings us to energy conservation, which says that energy is neither created nor destroyed, but it can move around from form to form. So we might do work on something to add energy to it, and that energy might be gravitational potential energy at the start plus some amount of kinetic energy at the start, and that's going to be equal to maybe work at the end, maybe friction changes some of that work done to heat. We might have gravitational potential energy at the end, and we might have kinetic energy at the end of this process. Okay, so this is a statement of conservation of energy for energy conservation for mechanical energy. Now this looks very menacing, but we're not going to always use all these terms because some of them may contain no energy, depending what we look at them and depending what we're doing. So let's see. Let's do an example here. Say, for example, I would like to know with what speed I have to throw a ball upward in order for it to reach a height of 45 meters. So let's see. At the beginning, I would like to know the kinetic energy, right? As soon as the ball leaves my hand, I'm not going to calculate the work done on the ball by my hand. I'm just going to look at it the instant it leaves my hand, and that's the amount of kinetic energy the ball has. And I'm going to look at gravitational potential energy at the end. So what's going to happen is all the energy is going to be kinetic at the beginning, and it's going to wind up being potential at the end. So we're going to go from the energy of motion to the energy of height. So let's see. So this is 1/2 mass times velocity squared is equal to mass times gravity times height. Now, interestingly enough, I don't have to know what the mass of the object is. Can everybody see that both terms on either side of the equal sign contain mass, the variable for mass, m? So if I divide both sides, and the equal sign says I have to do this to both sides, if I divide both sides by m, this variable goes away. So it says, really, that mass doesn't matter in this calculation. So next I'm going to multiply both sides by 2, and I'm going to get v squared is going to be equal to 2 times gh. The m is still gone. And I'm going to take the square root of both sides because I don't want to know what v squared is, right? I want to know what v is. So that's going to be the square root of 2gh. Okay. Oops, I've gone too far this time. Okay. So what I would like to do is I'd like to know how fast do I have to throw this object upward in order to reach a height of 45 meters. So let's start plugging that in. So 2, and I'm going to use 10 for gravity because, well, it's really 9.81, but there's no need to go crazy here. And this is going to be meters per second squared. And the height is 45 meters. And of course, I'm going to take the square root. So 45 times 10 is 450, times 2 is 900. So V is equal to the square root of 900. And the units, meters times meters is meters squared, and we have seconds squared. So that's going to be meters squared per seconds squared. So I'm going to take the square root now. The square root of 900 is 30, and the square root of meters squared per second squared is meters per second. So does everybody see that I even got the right units doing this? Okay, so what this is saying is if I have an object, regardless of mass, and I'd like it to reach a height of 45 meters when thrown upward, the minimum speed it must leave my hand with is 30 meters per second. Okay, anything less than that and it's going to reach a proportionally lower height. Okay, I hope this was a good introduction to work in mechanical energy.